Hello, let's have a look at unsymmetrical bending. How to get the stresses when you have a case of unsymmetrical bending. Unsymmetrical bending. Okay, so first thing that you should know is know how you have symmet. So you should know the things related to symmetrical bending. You have related to symmetrical bending. You have uh, the well-known flexure formula. Okay, and let me just draw a few things so that I can make it simple. These are things that you already know. You already know that. Okay, so this is a case of, let's say you have a rectangular section subjected to a load through its XY axis. Okay, basically the load acting through the Y. So the load which is acting through through the centroidal axis. This cross section is bisymmetric. It's a rectangle. It's symmetric. So you know how to find. You know that the stresses will look like this, and this is the neutral axis location. And in any at any place, if you want to know what the stress is, you just need to know what how far it is from the neutral axis, and you will also probably want to know stuff like Ixx and Iyy. So symmetrical bending is pretty simple. You have the general formula sigma by y equals m by I xx equals e by r if your moment is going to be acting about this axis, or in case it's going to be acting about the other axis, you just replace it with sigma by x equals my by I by y. So anyway, so basically you use the formula sigma equals m into y by I. So basically the same formula is going to help us with unsymmetrical bending. Only thing that you should know is know where unsymmetrical bending arises from. So unsymmetrical bending arises from two things. So it arises when your first place where it arises is if your centroidal axis are not your principal axis. Second place where it arises is in case your loading is not through a principal axis. Okay, so let's just look at cases where these things actually happen. This happens in any unsymmetric section. So basically, this deals with cross section asymmetry or unsymmetry. Okay, so if it's an angle section, you have your centroidal axis like this way, but your principal axis is going to be something else. Okay, so this is one case. The other case is even if you have a symmetric cross section. Okay, this is the cross section, but your load is not acting vertically perpendicular to this. It's instead of acting perpendicular to this, it's acting like this. Okay, so this is a case where you have symmetry, but your load is acting inclined. Your load is not through the principal axis, but it is through the it's inclined to the principal axis. So this is the second case where you have such a situation. uh, Next thing you need to know is how to get directions directions of moments. So the first thing is to get the uh, direction of moment vector. You use the right hand rule. Okay, just use the right hand rule. How you use this is, so you know for sure that from vector mechanics, you know that moment is nothing but cross product of displacement and force, correct? So you just adopt the right hand rule for this. So if this is the load vector and say that my distance for load times distance is the moment. So say the distance is measured this way. Okay, now use your right hand, point your middle finger in the direction of load, point your thumb in the direction of R, and the index finger gives you the direction of the moment vector. So it gives it to be in this direction. I used a double arrow because usually rotational things like moment couples are usually represented by double-headed arrows when you draw it in terms of vectors. So this becomes my M. Second thing, direction of sense of the moment. The sense of the moment is necessary for you to find out which parts of the section are in tension, which parts of the section are in compression. Anyway, so this is found using right hand thumb rule. Okay, so you know what the right hand thumb rule is, I hope. So if you just make a fist in your right hand, project your thumb outward in the direction of the moment arrow marks, and then the curl of your fingers will give you which way the moment acts. Okay, so this is how it. This is the thing that you need to know. The next, what you need to know is in cases like this, where your principal axis and your central axis don't coincide, you will need to find out principal axis. You'll have to find the principal axis of inertia and the principal moments of inertia. Okay, so this is given by simple formulae. So if you know Ixx and Iyy and Ixy, you can find out what this is. So this is given by Ixx plus Iyy by 2 plus or minus. This is just like your principal stresses formula in 2D. Ixx minus Iyy by 2 the whole square plus Ixy squared. If you add it, you get your major moment of inertia and minor moment of inertia. Then the inclination of this is given by tan 2 theta equals uh, 2Ixy by Iyy minus Ixx. All right. And what you should know is most of you may not have used this, but you need Ixy especially for unsymmetrical sections like this. So this is integral over the area xy dA. So when we do the problem, we'll see how to get that. Okay, so let's go keep going let's get proceeding with the let's proceed with the problem. So let's say this is my problem. Okay, let me try it big and neat. Um, does it look equal now? Yeah. So this is my angle. I'll make it an equal angle. Let's say 100 by 5 legs. . And what I have is I have a beam using this cross section and carrying 40 kilonewtons at 5 meter distance. What I do know is this is how the bending moment diagram is going to be. It's going to be a triangle. So this is going to be a triangle. Let me make it a nice triangle. All right. Yeah, and the value of this is going to be 5 times 40, 200. Okay. So what I will now mark out is the central axis will be somewhere here, possibly somewhere here. Okay. So this is my central axis, and I'll also try to mark out my. Okay, I'll do that later. So this is x, this is y axis, centroidal axis. I have my load which is acting through the y axis. Okay, so basically what I mean is if this is the cantilever and this is the centroidal axis, my P is acting right through that. So the right hand rule tells me the moment will be in this direction. Okay, if I take my z in this direction. Okay, so if my load is downward and z is this way, then the moment is this way. Okay, let's just keep it that way. So first step to do is to find the uh, see, the first thing that you need is I need to find all this principal moments of inertia and the principal axis of inertia. So before that I need to get everything in terms of the centroidal axis. So x bar is nothing but 100 times 5 times 50 plus 95 times 5 times so it's already 5 from here to here. So the center of this part, the center of this part will not be at 50, it will be somewhere. This is the centroid of this part, this is the centroid of this part. So here to here is 95.5, which means here to here is 47.5, and you have this extra 5, so 52.5 divided by 100 into 5 plus 95 into 5 gives me 26.86. And since this is an equal angle, you can be sure this will also be equal to y. So I have this is 26.86 and this is 26.86. So with this I can find out what uh, now to in when I try to find out the moment of inertia Ixx and Iyy, I need the distance between the centroid of each part to the centroid of each of these axes. Okay, so I can just, it's easy to find, you can just find out that this will be equal to 26.86 minus 2.5, which is about uh, 24.36, and that will be the case here too. And then I have from the center of this to here, so this will be here to here is 40 sorry, here to here is 52.5 and here to here is 26.86. So just subtract those two, you get 25.64, sorry, 25.64. And finally I also want from here to here. So that will be 50 minus 26.86. Wait a minute. That will be just a minute. 50 minus 26.23.64. Okay. So I get all of this. Now I can find out what is Ixx and Iyy. Ixx equals Iyy. Use the parallel access theorem. So 100 into 5 cube by 12 plus 100 into 5 into, it's about x-axis, so 24.36 downward plus 95 cube into 5 by 12 plus 95 into 5 into, so here to here it's a plus 25.64. This minus and plus come depending on whether it's on the below or above. Okay, positive x or positive y or negative y direction. So this is 967.225 mm power 4. I then go to IXY. So basically this is easy to find. Just multiply the area of each component with its coordinates. So if it's the 100 into 5 area, multiply it with uh, plus 23.64, and you also multiply it with, sorry, this is 23.14, I'm sorry, 14. So minus, you multiply it with 23.14, positive because it's towards the right, and minus 24.36, plus the next area 95 times 5 uh, into minus 24.36 and plus 25.64, and minus 24 point. So this gives minus 578.825 mm power 4. Product of inertia can be negative. It can. The next job is to find my principal moments of inertia, IUU and IVV. So use this formula, substitute the values of Ixx, Iyy and Ixy. You add it, you get IU, you subtract it, you get IVV. Okay, just make the substitution. So I'll have 967.225 plus 967.225 by 2 plus or minus root of, this will actually become 0, plus this thing square, minus 578.825 square. So this gives me IUU is 1546080 and IVV is 388. That's what IVV is. Okay, and the direction, you can guess it's symmetric, so it will be 45. But if you want, you can calculate it using this formula. So theta is half tan inverse 2 tau x by 2 into minus 578.225 by Iyy minus Ixx, which will be 0, or half of tan inverse infinity, or so half of 90 degrees, which is 45. So my centroidal axis my principal axis are like this. Okay, so this becomes u, this becomes v, this becomes 45 degrees. Okay, so the next thing that you need to know is the next thing you need to do is you need to resolve your moment. Resolve moment into u and v components. So let's go ahead and do that. So this is my u axis, so this will be my u component mu, and this is my v axis, this will be my v component. Sorry, this will be my uh, this will be my v component mv. This is for this is 45 degrees. Okay, that is 45 degrees. So mu is m cos 45, mv is m sin 45. Since sin 45 cos 45 are same, you get 200 sin 45, 141 sin 45 or cos 45. Okay, whatever it is. So both of them will be 141. So this, how does this actually cause moments? That is the next thing that you need to find. What kind of stresses do these cause? So let me just draw the angle. I'll draw it very light because I want to. The angle is not the important thing here. So anyway, just so if this is my, no, I just want to go ahead and draw my principal axis. So principal axis. Okay. So this is u. This is v. You have mu this way, mv this way. Now come back to your symmetrical bending. Now you know here that over here, if I have a moment acting this way, if I draw it in cross section, so this moment is what I've shown here. This is the cross section view. This is the elevation view. So when you have this kind of a moment, you know that this is a sagging moment. Okay, and you identify that since this represents a sagging moment, all parts here will be compressive, all parts here will be tensile. Okay, here it is easy to do because your axis is horizontal and you have only one moment, you don't have two moments. So you say that the stresses caused by the moment on all parts above here is compressive, all parts below this axis is tensile, and that is what was indeed shown to you here. It directly depended on the distance from the neutral axis. Now the same thing happens over here. The same thing would happen over here. Okay. Now what you need to find here is there are some things which these moments will cause compression on some parts of the ankle, tension on some parts of the ankle. Similarly, mv will cause compression on some parts and tension on some parts. So the job is to find out where it's compressive, where it's tensile. So let's just imagine that these are all the quadrants of the uv coordinate system. These are all the quadrants of the uv coordinate system. So in each quadrant you will have a certain combination. So for example, for this I need to know the sense of my moment. Without the sense of the moment I cannot do it. I know that for this moment, it's keep your right hand thumb rule. You see that You see that your thing is going this way, and keep your finger over here. You see that it goes. This is how your fingers will curl over. Now, what you can observe from here is the parts which are the parts to which this arrow mark is pointing. Those are compressive. The parts away from the arrow mark are tensile. The same thing can be applied over here. So, if you take MV, this side, this quadrant and this quadrant are all on top of this V axis, or this arrow mark is pointing to the parts on top of this V axis. So the stresses caused by MV here are positive, and these two quadrants are on the opposite side of the arrow mark. Okay, it's on the opposite side of the arrow mark. So therefore, um, MV is negative here in this quadrant and this quadrant. Oh, one thing that I should tell you is when you draw this, when you draw this, say for example, this is the moment vector, and when you draw uh, the curl, please draw it completely. Okay, draw it like this such that it completes the whole thing. Okay, please don't draw it like, don't stop it like this. If you stop it like this, you will get confused whether these the parts below are negative or whether the parts above are negative. You don't stop it with a half arrow mark. Make the full thing complete. And the best way to imagine where to place this arrow mark is, imagine that this arrow mark is your fingernail. So if the arrow mark is supposed to be a fingernail, that will tell you where to actually draw the arrow mark. Okay, that will tell you where to draw the arrow mark. Okay, so anyway, coming back to this. So if I apply a similar concept to mu, I see that here will be mu positive. Here also mu positive. And here I have mu negative. Mu negative. Okay, so this is what that I need. Next thing that I need is if you look at this, this formula is in terms of the centroidal coordinates y and x. You are no longer dealing with y and x coordinates. You are dealing with u and v coordinates. So you have to transform your coordinates to from xy to uv. Okay, you need to transform it. And what you can be sure is, if you draw your x leftward, x rightward, y upward, and if you rotate your axis by counterclockwise direction from x, then you can use these formulas for the transformation. You can use u equals x cos theta plus y sin theta, and v equals minus x sin theta plus y cos theta. And let me say that I want the stresses here on the corner and the edges. Okay, so here I say corner is corner xy is, so this is the point. So it's 26.86 downward, 26.86 leftward. So both are minus 26.86 comma minus 26.86, and the theta is, it's been rotated by 45 degrees. That's your inclination of principal axis. So this gives you just substitute minus 26.86 for x and y and 45 for theta. So you will get minus 37.98 for u, and v will be 0. Is it right? Yes, it's right. This is the v-axis. The corner is passing through the u-axis. So v is 0 here. So v is this point corresponds to this point lies on the u-axis, which means v is 0. So this is right. Let me say that I also want it for the edge. Let me say this edge. Okay. So that edge corresponds to an x and y of x comma y of. So x is 100 minus 28, 26.86, which is 70. How much? It's 73.14. 73.14 and minus 26.86, theta 45 as usual. So u here comes to be plus 32.72 and v comes to be minus 70.7. Okay, so let's try to find the stresses. So sigma equals mu, it's mu into uh, v by iuu, mv into u by ibb. Okay, or let me not use u and v. I'll tell you why I don't want to use the letters u and v here. Okay, so say this point. So this point I found u is 32.72, which means this point is 32.72 from here, and this it's also from the v-axis. It's minus 70.7, but when you talk in terms of distance, you don't use the sign. Okay, so I'll say that anything measured along the u direction, I'll name it as c. Anything measured along v direction, I'll name it as d. So let me say it is we use c and d. The reason that I'm using c and d, so that I don't by mistake include the minus sign from this. The plus or minus sign for these terms will be decided based on where in this quadrant they lie. Okay, it is basically based on where. Okay, now coming to the first one. U is negative, v is 0. Okay, u is negative, v is 0. Okay, so let's come by this over here. So basically that is somewhere on this quadrant. Okay, it is on the axis. I'm not really sure whether I should use this quadrant or this quadrant. So the answer is you can use either of it. Let's say that let's take this quadrant. Okay, so the mv should be negative. Okay, mv is negative and mu is positive in that quadrant. Okay, so I use those signs. I mean, not mv is not negative. The stresses caused by mv is negative. The stresses caused by mu is positive. Okay, so both of them are 141. So 141, it's 141 into 10 power 6 Newton mm. I will use the 10 power 6. So because everything is in these are all in millimeters. I is in millimeters. So 141 into 10 power 6 into c is, so for this case what is c? C is 37.98. 37.98 divided by IUU 1546080. Okay, mu into, I'm sorry, mu into, it's the perpendicular distance, right? So mu means it should be with C, mv should be with d. Sorry about that, because d is perpendicular to u and c is perpendicular to v, so it should be this. Uh, so here, c is, this is 0. Yeah. Uh, so mu into d by d is 0 to 0 minus mv is 141 into 10 power 6. C is 37.98 divided by 388 430. Okay, so evaluating this, I get just a second. 37.98 divided by 388430 into 141 13787. Okay, so I get about quite a large number, 13. So I get the stress here is quite high, but that's what you get. So coming to the next point, uh, this corner. So mu d by iuu, mv c by IBV. What signs do I use? It's on this quadrant. MV is positive, mu is negative. MV is positive, mu is negative. So therefore you get 141 into 10 power 6. D is 70.7 by 1546080 and minus 141 into 10 power 6 into 32.72 by 388430. So this is 5429 Newton per mm squared. Okay, this is what comes, and therefore you can imagine that this point is, no, it's a symmetric section, and this point is the equivalent point of this, except that it is on this part. So therefore the stress, it will be symmetric, and stress there will be rather minus 5429 Newton per mm square. Okay, so the next thing what you can try to find is, um, so this is the way that you can actually try to find out the stresses at any given location of a beam which is going undergoing unsymmetrical bending. So what happens in the case of monosymmetric or bisymmetric sections? So if you have monosymmetric or bisymmetric sections, uh, like the channel, uh, I'm not going to do a problem, I'll just tell you what differences will occur. say your channel like this, which is obviously symmetric about x-axis. What you should remember that is, if your load acts through either this axis or acts through this axis, you will not have unsymmetrical bending, it will be symmetrical bending. If you want to have unsymmetrical bending here, you definitely need your load to be inclined, otherwise you will not have a case of unsymmetrical bending. Okay, and your moment vector will be rotated by the same angle. What you will also have is, you won't have different principal axis of inertia, you will have the same principal axis of inertia, and you will have only Ixx same as Iuu, Iv. V will be the same as Iyy. Okay, so and you don't no need for you don't have any need for xy to uv transformations. You simply just need to get m sine theta and m cos theta components. Okay, basically you just need the components along this direction and the component along this direction, and then you can just go ahead and you can say that you can just mark out the same and find out which moments cause positive or negative stresses in each of these four quadrants, as you did over here, and you can just assign the signs to when you're adding up the stresses. Okay, so this is what you will have to do in case you have a monosymmetric or bisymmetric section with an inclined load. It's easier because you don't require these steps. Okay, you can just directly resolve the moments and get what the stresses are. Okay, and it's also possible that in even in unsymmetric section, there's a possibility that you do have the possibility that um, this is a bit complicated. This is a little more. This is probably the worst case that you can get, where you have. Um, so this is your central axis. You, in case you have a situation where your load is inclined. In this case, so what basically you're going to have to do is nothing much, except now you're going to find your uh, let me draw my principal axis. Just a minute, I'll make it a little more obvious what you have to do. This looks a bit strange. Okay, theta. Okay, now you will get your principal axis like this. So the only thing is, when you now try to resolve your moments, so you will have to resolve it with respect to this whole angle. Okay, the resolution has to be done with respect to uh, unfortunately it has to be done with respect to this angle. Okay, you just have to get the angle, add it, and then do the m sine theta and m cos theta. That will take care of your issue when you have a case, the complicated, where there is both section unsymmetry and loading unsymmetry. Okay, so this is how you can do that. So other thing that what you can actually try to do is, you can also get from uh, you can also try to find out what the position of the neutral axis is. So to find the position of the neutral axis, what you can do is, you can use one of these formulas. Okay, and you can just equate stress to zero, and that will give you the position of your neutral axis. Okay. So anyway, this is the end of the lecture. So I hope this gives you a better clarification on how to solve unsymmetrical bending. And this is a more this is the actual approach where you don't have to remember formulas, because the problem with formulae which are given in books is the formulae are very specific with respect to the coordinate systems that you use, and very specific with respect to the sign conventions for the moments that you take. Okay, if any of those changes occur, which you may do, especially when you compare different books, some books will use a certain sign convention, and if you use their formula for something you read from another book, you're going to not get the right answer. So instead of remembering formula, no, this is the more exact way of doing it, even though it looks a bit more difficult to do. Okay, so I'll come with another video later. Thank you for your attention. Bye.